This is a nice review paper. Well, it's a perspective by some prominent names like Sarah Kang and Matt Collins. Matt Collins has done a lot of work on, climate change, processes, dynamics, patterns, IPCC. Sarah Kang has done a lot of work on how the ITCZ and the warming patterns are related, and they have written this perspective on the possible shift in controls of the tropical Pacific surface warming pattern. This has been a debate, the warming pattern, whether the eastern Pacific is warming less or even cooling, and is that what is expected under global warming, because that could have big consequences for how much heat goes into the ocean and what the rate of global warming will be. And Richard Seeger keeps writing about how the models are failing to capture that. In fact, back in 1998 or so, Richard Seeger had predicted actually that the global warming pattern will look like a La Nina. In other words, the eastern Pacific will warm less. This is a rather long paper, so as usual I'm going to try to keep it brief, but I'll make it maybe 2 podcasts because I don't want to miss too many things. So the paper is lovely and you should read it. So remember that I'm just doing, picking just the main points. So if you want to all the points, then obviously you want to go and read the paper. And there are a tremendous number of very useful references as well. Changes in the sea surface temperature pattern in the tropical Pacific modulate radiative feedbacks to greenhouse gas, forcing the pace of global warming and regional climate impacts. So basically has global consequences. The Western Pacific, which relates to how the East Pacific does with the SST gradient and the wind response and the positive feedback, will have radiative forcing feedbacks because West Pacific has all the convection, a tremendous amount of clouds, and of course the pace of global warming is what I mentioned, with how much heat goes into the oceans, and regional impacts come through all the teleconnections. Therefore, elucidating the drivers of the pattern is critically important for reducing uncertainties in future projections. However, the causes of observed changes over recent decades and enhancement of the zonal SST contrast, coupled with a strengthening of the Walker circulation, are still debated. If you cool the Eastern Pacific, SST gradient should get stronger, and then the positive feedback should get you stronger Walker circulation in the Pacific. But there was an argument made that it's weakening, so then that debate has exploded into showing that actually the Walker cell is doing something that we didn't expect, let's say. Okay, so here we'll read more details, so don't worry too much. Here we focus on the role of external forcing and review existing mechanisms of the forced response, categorized as either an energy perspective that adopts global and hemispheric energy budget constraints, or a dynamical perspective that examines the atmosphere-ocean coupled processes. So is it a global balance that is controlling the Pacific response, or is it coupled dynamics in the tropics that are affecting the global response, right? And when we say external forcing, we basically mean human activities and greenhouse gas increases, which affect the radiative balance to begin with. We then discuss their collective and relative contributions to the past and future SST pattern changes and propose a narrative that reconciles them. Although definitive evidence is not yet available, our assessment suggests that the zonal SST contrast has been dominated by strengthening mechanisms in the past, but will shift towards being dominated by weakening mechanisms in the future. So this is a conjecture, an educated guess, let's say. Finally, we present opportunities to resolve model observations discrepancies regarding the recent trends, and as I mentioned, models are not doing well in capturing the observed trend. Okay, a lot of text, but I will read the text anyways because it's all, I have reduced the text, but it's still a lot of important points to be made. Earth's surface temperature has warmed by about 1.1 Kelvin since pre-industrial era, and this warming has been unequivocally unequivocally attributed to human-induced emissions of greenhouse gases. The past warming has caused changes in many aspects of the climate system, including sea level, the cryosphere, land surface environments, regional precipitation patterns, and weather extremes, all affecting human society. Of course, these regional impacts largely depend on the spatial pattern of tropical SST changes, a primary driver of the large-scale atmospheric circulation, especially in the Pacific. However, considerable uncertainty remains in the physical origins of the multi-decadal scale SST warming pattern. So we are saying two things there. Warming pattern, so we talk about trend since the Industrial Revolution, and then we are saying multi-decadal scale SST warming pattern, because the warming patterns are shifting, which is essential for them to say there may be a shift in the controls coming from strengthening mechanisms to weakening mechanisms, right? The tropical Pacific SST trend over the recent decades reveals warming in the west and cooling in the east, intensifying the climatological zonal SST contrast that I mentioned. The period of 1979 to 2013, a focus in many previous studies, shows the largest strengthening trend in the equatorial zonal SST gradient since 1900. The trend in terms of the pattern and the magnitude is similar to the period if the period is extended or when the period is extended to 2022, except for the lack of cooling in the northern subtropical eastern Pacific, so towards let's say Gulf of Alaska, actually subtropical, so towards the ITCZ, California, and so on. We'll look at the map in a minute. The index of the equatorial zonal SST gradient shows a linear trend of 0.21 and 0.17 K per decade for 1979 to 2013 and 1979 to 2022 respectively, so it damped a little bit, still in the same direction, indicating that the mean zonal SST gradient has strengthened by approximately 30% relative to the 20th century average. So zonal gradient is gone from 0.21 to 0.17 K when you extend the period. The strengthening of the zonal SST gradient accompanies an enhanced Pacific Walker circulation PWC, which is identified using different reanalysis data sets. The magnitude of the trend depends on the exact period and the length chosen. But the observations reveal that the recent strengthening of the SST gradient and PWC has lasted for more than 4 decades, even after the 2015-16 El Nino, which is very strong, which warms the east, and that has not managed to damp the east-west gradient. And here reanalysis, if you don't know what they are, blended model and data products, dynamic interpolation of past data to fill the gaps and give you a graded product. There are many details that you don't need to worry about. Even the triple dip La Nina in 2020 to 2022 hasn't changed the trend. The recent multi-decadal SST trend is not subject to observational uncertainty, unlike the centennial trend, which has large uncertainties. Despite the small difference in the magnitude of the SST gradient trend across multiple SST data sets, they all indicate the strengthening of over the recent decades, and this observational uncertainty is small compared to the discrepancies with climate model simulations explained below. Okay, the tropical Pacific, I'm keeping track of time so that I don't want to make each podcast too long. Since we'll make 2 anyways, we'll make it about 20 minutes each, let's say. The tropical Pacific SST warming pattern regulates regional precipitation changes through the warm get warmer mechanism that we'll read about in a minute, and alters tropical cyclone tracks, which has been discussed a lot. Recent studies also show that global climate feedbacks vary depending on the tropical Pacific warming pattern. This so-called pattern effect describes the influence of the SST warming pattern on the Earth's energy budget at the top of the atmosphere, leading to the recognition that the estimates of climate sensitivity is affected by the SST pattern change during both the historical period and future with further warming. So overall, how the energy balance is happening in terms of losing thermal energy and trapping additional thermal energy because of external forcing or increased greenhouse gases depends on how the energy is distributed as well. Hence, it is of critical importance to attribute how much of the pattern is due to radiatively forced responses and how much is due to internally generated climate variability. Okay. As the Pacific SST trend pattern for 1979 to 2013 bears a similarity to the interdecadal Pacific oscillation, it's an interhemispheric pattern, a decadal interdecadal mode of natural variability IPO says that the past SST pattern change can be explained primarily by internal variability. So if the warming pattern you are getting looks like a natural mode, then you have to say, are the two being conflated? Indeed, some individual realizations in large ensemble coupled model intercomparison project phases 5 and 6, so CMIP 5 and 6, historical simulations can capture the observed strengthening of the zonal SST gradient and the enhanced PWC. However, a thorough analysis of large-scale ensemble simulations shows that the SST trend for 1979 to 2020 is very unlikely, so less than 5% probability to be explained by internal variability alone. You can do attribution exercises by taking out greenhouse gas forcing and showing that this is above the internal variability or this is not explained by just internal variability. Furthermore, the SST trend pattern for a more recent period, such as 1979 to 2022, has deviated from the canonical IPO pattern, as we'll see in a minute. This indicates that the part of the observed trends in the recent decades may be explained as being a response to external forcing, which may not be well represented in the climate models. Unlike observations, models tend to show a weakening of the gradient over these periods, and it continues into the future projections with increasing magnitude. So there is a very fundamental difference between observations and models, and we are saying the SST gradient in the tropical Pacific has global consequences dynamically and radiatively. Then we are saying models are not doing that correctly, so you have to be very careful about future projections, right? Given the above discussion, we raise two main issues in this paper. First, I jumped a little bit ahead here, we seek to evaluate the forced mechanisms that strengthen the zonal SST gradient and the PWC in recent decades, and then to reconcile the past strengthening with the future weakening as simulated by climate models. Second, we seek to identify the processes that are missing or not well represented in models and discuss how we can resolve the model observation discrepancy. While noting a potentially important contribution of internal variability, here we focus on the forced responses because they are the most relevant for increasing confidence in future projections. So let's look at figure 1 here before continuing. So this is the pattern we're talking about. There is this kind of a large IPO type interhemispheric pattern with this coming down here, and we are mostly focusing on the tropical Pacific with less warming or even cooling on this side and rapid warming on this side. If you already remember the Bjerknes feedback kind of thing, if you increase this SST gradient, winds should get stronger because high pressure, low pressure situation, that would cool this further and amplify the pattern, right? So that's what we are talking about, and this is also referred to as the ocean dynamic thermostat, because if this cools here, this is where the ocean is taking up heat, so more heat can go into the ocean and modulate the global warming rate. So it's like a thermostat. As you increase the external forcing, there is a mechanism which can damp the warming rates. But remember that El Nino belches out a lot of this heat, but over decadal time scales that heat gets redistributed in the ocean, so it's not all belched out by the El Nino. If you look at the longer period, 1979 to 2022, the pattern changes a little bit, but the east-west SST gradient is still there. Remember, this was around 0.21 and this is around 0.17, sorry. And the IPO pattern is beginning to be modified. This is the classical IPO pattern and so on. So if you look at the trends from 1900 to 2020, remembering there are uncertainties in the longer data. So 35-year trends are shown here, and in the thinner line, so let's say Oops, this is the 1979 to 2013 trend here, 1979 to 2022 trend, which is a little damped. So you are looking at interannual variability and multi-decadal variability. So this is what we mean by patterns versus decadal natural variability, which is the IPO here, right? So the Walker Circulation Index, you can see how it is defined, also shows slight differences, but they all agree with each other. That's the main point. Okay, so I won't read the details here, but basically we are looking at the two trends based on extended reconstructed, so there is certain products. C and D are time series of the zonal SST gradient in the equatorial Pacific, defined as SST differences between east and west, and the Walker Circulation Index equivalent to conventional Southern Oscillation Index, defined by the zonal contrast of sea level pressures between eastern and western equatorial Pacific. So, Southern Oscillation is between Darwin and Tahiti, but this has gone into the topics, but they are equivalent, high correlation between them. So, let's go back and read the analysis to say why we may be moving from a strengthening feedbacks to weakening feedbacks in terms of the future response of the SST gradient in the Pacific and the controlling mechanisms, right? Energy budget perspective then says energy budget equation at the top of the atmosphere used to estimate the equilibrium climate sensitivity and the transient climate response consists of changes in global mean quantities of radiative forcing, surface temperature, energy imbalance equivalent to ocean heat content change, and the climate feedback parameters. For a lot of very nice references you should read up if you are interested. For a given increase of radiative forcing due to the increasing concentrations of atmospheric CO2 and other radiative forcing agents like methane, N2O, etc., the climate system reacts by adjusting with surface warming, leading to increased radiative flux to space at a rate defined by the climate feedback parameter. In reality, the global mean energy budget is not independent of the spatial pattern of sea surface temperature change. All the feedbacks determine how much stays in the ocean and how much has to be adjusted by throwing it out to space. On the one hand, the pattern of temperature change modulates the climate feedback and therefore the equilibrium climate sensitivity and the transient climate change response as well. On the other hand, uniform radiative forcing can give rise to spatially non-uniform patterns of surface temperature change through several pathways we'll look at in a minute in the figure. In the transient response, the surface warming pattern is also affected by the ocean heat uptake changes, which can be explicitly coupled to the pattern effect in a simple theory, but it's difficult to distinguish between them in observations and climate model simulations. Sounds complicated, but essentially we are saying that even if you had, let's say, 10 watts per meter squared, in this case it's a couple of watts per meter squared, increase in net heat flux the ocean sees, the ocean will not produce a uniform warming pattern because the winds respond, ocean responds, and then there can be positive feedback like we talked about. Oops, which way am I going? Like we are talking about here, and that determines the overall pattern in addition. So you start the feedbacks, then redistribution of ocean heat happens, atmospheric response happens, warming pattern happens, right? Warming pattern changes happen. So looking at different constraints on the energy budget, you have to look at constraint on the hydrological cycle as well, and it has been looked at extensively, as you will see with the references here. A theoretical argument regarding the global mean atmospheric circulation change in response to a global warming in response to global warming has been built on the basis of the hydrological budget, which consists of changes in precipitation, column water vapor, and vertical mass flux at the top of the boundary layer. The last of these determined by the competition between the first two, as we will see. A global precipitation cannot as global precipitation cannot increase more than global water vapor, mass flux has to weaken by 4 to 5% per degree Kelvin warming. Although this budget is an approximate form, assuming that the precipitation efficiency is unity, the predicted change in mass flux has been supported by both idealized and realistic climate change simulations and is used to interpret the centennial slowdown of the tropical circulation in the historical period. So that sounds very complicated. Basically, because the atmosphere is warming, the increase in water vapor demand, let's say, and that water vapor has to rain out for balance at some time scale, but rainfall in a global average releases condensation heat, which is part of the radiative balance. So that gives you constraints on how much warming is happened, how much water vapor increase happens through Clausius-Clapeyron, how much of that gets converted into rainfall, and why that has to then affect the circulation, because you cannot keep pumping water vapor unless you rain it out. So there are these constraints we have to worry about. However, it was stated in reference 31, which you can look up, that the reduction in the global mass flux does not necessarily entail a weakening of the mean tropical circulation. This was the key battle that started by a paper by Gabe Vecchi, I think, which said Walker circulation is weakening, and it turned out actually it's strengthening, and so on. Indeed, several studies reported that the mass flux has reduced, whereas the PWC has strengthened over the past decades. So PWC is just the Pacific Walker circulation. Lots of rain in the West Pacific maritime continent. It's called the boiler box. So is it controlling the global water vapor flux, or can it strengthen and still you can have flux changes that can explain radiative balances? Indeed, several studies reported that the mass flux has reduced, whereas PWC has strengthened over the past decades. This apparent inconsistency is reconciled by the SST pattern effect on the PWC, but not on the global mass flux, and by the fact that the weakening constrained by the hydrological budget has not emerged at the present global warming level. An alternative explanation to this constraint has been provided using the moist static energy budget called the anomalous gross moist stability GMS mechanism, associated with the rise of tropopause due to surface warming. Roughly following the moist adiabat, GMS, global moist stability, is expected to increase, which acts to weaken the PWC. Recent theoretical advances demonstrated that the two mechanisms embody essentially the same physics. In other words, we are saying how complicated the system is. PWC is not just constrained by local SST gradient, but it cares about the SST pattern, because there is also a Hadley cell to worry about, and there is these fluxes of water vapor up, precipitation down, radiative balance overall have to be reconciled. Okay, I'll read one more and then we'll move to the next podcast. This is already quite long. Differential evaporative damping, another energy perspective mechanism that could explain the weakening of the zonal SST gradient in response to global warming, has been proposed on the basis of the surface heat budget. The so-called differential evaporative damping mechanism can be induced by uniform warming imposed on the climatological SST pattern. As surface evaporation depends on the total local SST, the damping of the same SST anomaly due to latent heat release will be larger over the warm pool than over the cold tongue, leading to a weakening of the zonal SST contrast. So Clausius-Clapeyron is exponential dependence of humidity on temperature. So obviously the response is stronger on warmer temperatures than on cooler temperatures, even though there is a linear dependence on wind speed. So if you warm less or cool here and warm more there, you have to worry about the differential evaporative damping as well, and not just the pressure gradient, wind response, and the positive feedback. See how complicated it is. Okay, the efficiency of this evaporative damping mechanism has not yet been identified in observational records, but this mechanism has been clearly detected in idealized model experiments in which ocean dynamics are excluded, and explains about 30% of the SST gradient weakening in response to imposed CO2 forcing in a fully coupled model. Okay, so if uniform flux can indeed increase the SST gradient and wind feedback can strengthen it, the evaporative damping can weaken the gradient. So the net balance or net trend of the gradient will depend on this feedback as well. So we'll come back and look at additional mechanisms that have to be considered before we move on to why they are proposing, the authors are proposing that maybe there will be a shift in the control mechanisms as we go into the future, as opposed to what's been happening now with strengthening feedbacks. Okay, so see you in the next podcast. As I said, this will be a long one, but it's a very important topic, so I want to make the most important points, even though I'm being brief and cutting out a lot of the text, beautiful text that you should read. Okay, see you in the next part of this topic.